Hello everyone, welcome to our webinar today. The topic for today's webinar is sodium the new lithium? How table salt might save the energy storage industry. And we've got an excellent panel of guest speakers with us today, but before I hand it over to them, I'd like to go over a few webinar logistics. We're using a newly updated version of GoToWebinar, so if you have any feedback for us, please let us know in our post-webinar survey. All attendees are in listen-only mode, so your webcam and your microphone are disabled. If you would like to submit questions and comments, you can do so via the questions panel. Speaker bios are available to read in the materials section, and automated captions are available. Lastly, this webinar is being recorded. We will email you a webinar recording within 48 hours, and it will also be posted on CISA's website at cisa.org/webinars. And we are sharing a few videos today. If you are dialing in rather than viewing it on your laptop, you may have some difficulty viewing the videos, but they will be included in the follow-up webinar recording that we will email to you after the webinar. And with that, I'd like to pass it over to our host for today's webinar, my colleague Todd Owinski-Paul.
Thank you, Zareen, and welcome everybody to another in the long-running STAP Energy Storage webinar series. I will give a brief introduction of the program, and then I will briefly introduce the speakers, and then we'll be off. So if you could just advance the slide, please, Zareen. Clean Energy States Alliance is a nonprofit. We are based in Vermont, but we work with states across the country. Essentially, we are a membership organization for state energy agencies that are involved in managing clean energy programs of all sorts. And we support them in that effort, and we also help them with things like basic research and knowledge sharing and so forth. You can see on this slide the logos of our member states. Next slide, please. One of the things that we do in this in CISA, aside from just basic member support for the states, is we do specific projects around different technologies. This particular webinar series is part of the STAP program, which is the Energy Storage Technology Advancement Partnership. We conduct this under contract to Sandia National Laboratories with support from DOE Office of Electricity. And the image here is a ribbon cutting at a battery project in New Mexico, because one of the things that STAP is engaged with is to bring states to the table to partner with the National Lab, DOE, OE, and other partners to install demonstration energy storage projects. We also do lots of other things, including webinars like this one, reports, case studies, conference presentations, and so forth. Next slide, please. So before going forward, I want to thank Dr. Imre Gyuk, who we're fortunate to have with us today, and Waylon Clark. Dr. Gyuk is with DOE Office of Electricity, and Waylon is with Sandia National Laboratories. Next slide, please. So I want to introduce the speakers in order of who will be speaking first. So we'll have Dr. Gyuk give us some introductory remarks. Then we will get an overview of sodium-ion batteries from Ramesh Koripella from Sandia National Laboratories. I hope I pronounced your name correctly, Ramesh. Then Alex Bates, also from Sandia, will talk about safety with regard to sodium batteries. And then we have Jack Pouchet from Natron Energy, who will talk about commercial markets and applications. And then, of course, we will take all of the questions that we have time for, and hopefully we'll have a lot of them, and we'll have a good, lively question and answer and discussion period. So without further ado, I will hand the microphone over to Dr. Gyuk.
Okay, can I have my slides, please? Thank you. So we are going to talk about is sodium ion the next lithium? Or my title, Decarbonization Needs Diversification. Now, next please. Yeah. The point is that lithium has been with us for a few years, and it has proved to be excellent for short duration applications, less than 4 hours. But what it is not good for is medium and long duration energy storage. It simply isn't cost effective. Next, please. Now, there's another point. Fairly soon, the available lithium is going to be needed for vehicle electrification. And there's a reason for that, because electric vehicles require the high energy density that lithium batteries can provide. And electric vehicles can pay for the extra amount, whereas stationary batteries cannot. And here is the graph. If you put all the various types of energy storage lithium reserves into a pot, it still isn't enough for the demand. And by 2029, demand will outstrip supply. Obviously, we have to do something. We are looking for batteries using earth-abundant, domestically available, inexpensive materials. But at the same time, they should show performance characteristics similar to lithium ion. Doesn't have to be exactly equal, but they should be at least in the same range. And indeed, we can do that. Next, please. Here is the chart of elements that are available. And where we want to be is up in the dark green of rock-forming elements. That means earth abundant. And you can see that sodium is right in there between oxygen and silicon, which is just sand. So definitely earth abundant. Next, please. Is it less expensive? It certainly is. Lithium carbonate, the raw material for lithium batteries, is roughly $20,000 per ton. It varies considerably, but that seems to be the lowest price. Sodium carbonate, on the other hand, is $332 per ton. That's 2 orders of magnitude less. And by the way, it's lithium carbonate. It's not, well, it's sodium carbonate, not table salt. Table salt is sodium chloride, and that's a different thing altogether. And what is really good is that there are 135 billion tons of mineable sodium carbonate available in the Green River Basin of Wyoming, right here in the US. If we look at characteristics, here we have a map of cycle life and capacity. Rather inconveniently, black on black, lithium LFP and lithium NMC as for comparison. But as you can see, the various types of sodium-ion batteries are up there with the lithium-ion batteries. That includes in red the layered oxide batteries, and in green, or something like it, the polyanion batteries. Some of those factories are fairly large. In fact, they have become gigafactories, just like lithium. And we have in the US Natron, and in China we have CATL and BYD. India is working at it with a company called Reliance, which has put a lot of money into it and has bought up Radion from Britain. And there is Altris in Sweden, if it's still going after sodium ion. And there are other companies as well, both in China and elsewhere. So as a summary, sodium ion batteries indeed still lag lithium ion batteries with respect to performance, but they are competitive on price and can be sourced domestically. I am confident that they will find their market when lithium becomes scarce and is used mostly for electric vehicles. And that's all I want to say. And now we go on to the next speakers.
Okay, thank you, Dr. Gyuk. My name is Ramesh Koripella. I work at Sandia Labs in the energy storage demonstrations team. At Sandia, our resident expert on sodium-ion batteries is Eric Sporky. He is an assignment at the DOE office, so I'm covering for him, giving introduction on the sodium batteries. And then followed by Alex Bates from our labs. He's going to talk about safety aspects of the lithium-ion battery, followed by Jack from Natron. He'll talk about commercialization application of the sodium-ion batteries. Okay, let's go to the first slide. Okay, Jarin, maybe you want to move it. That may be easier. I'm having difficulty here controlling it. Okay, there's a lot of excitement about sodium-ion batteries. As Dr. Gyuk pointed out, it is made with earth-abundant materials that are lower in cost and also safe too. There are no significant thermal runaway problems, but take that with a grain of salt because Alex will present more info on that one. These batteries can be shipped with zero charge state, so it's much safer during shipping versus lithium-ion battery always have to have certain charge in it. There are many different types of sodium batteries. They're low temperature, high temperature, and different chemistries. So what are the differences? And how do they compare with lithium-ion batteries? And what is the current state of commercialization? So we'll touch on these aspects briefly in this presentation. Go to the next slide. So this is a brief outline. First, I'll touch on some of the high temperature molten sodium batteries, followed by low temperature sodium ion batteries that are analogous to lithium ion batteries. We'll cover different chemistries, pros and cons, typical issues, and the current state of development. Next slide. So there are distinctly two different types of sodium batteries. One are high temperature, one are low temperature. These high temperature batteries are also called molten sodium batteries. So these are commercial, and some are still in the R&D stage. Sodium sulfur batteries, sodium metal halide, they are both commercial, and the intermediate and low temperature sodium batteries are still in the R&D stage. Whereas low temperature sodium ion batteries, these are, as I said, analogous to lithium ion batteries. They are in the, some of them are early commercial, some to pre-commercial stage. Again, there are different types in these batteries also, based on type of anode and cathodes they use. For example, in the cathodes, some use layered oxides, some are polyanion, some are Persian blue analogs, and the cathodes, some of them use hard carbon, some use Persian blue analogs. So we will touch on them briefly. Go to the next slide. Sodium sulfur batteries. This is one of the oldest battery chemistries, developed in 1960s at the Ford Motor Company for automotive applications. This is a reaction between molten sodium anode and molten sulfur cathode, forming sodium sulfide. So this molten sodium is contained in a solid ceramic tube made of beta alumina. So that's also the electrolyte. This battery requires high temperature operation, at least close to 300 degrees C, because the beta alumina is a sodium ion conductor, but it requires a temperature close to 300 degrees C for the conductivity. At low temperature, it's not conductive. At those temperatures, sodium is molten because its melting temperature is 98 degrees, and also sulfur is also molten. Melting temperature is 118. These beta alumina is typically made in a tubular form with a closed-end tube because it's easy to contain these molten metals inside. In the reaction, when you discharge this battery, they form sodium. First, you form sodium pentasulfide followed by different polysulfides. But some of these, if you discharge lower, some of these polysulfides are not really reversible. For that reason, they discharge it only up to 1.74 volts, and then they cycle it between 1.74 and the open circuit voltage 2.08. Because of that one, it loses some capacity, but still these are pretty good batteries. Go to the next one in a commercial stage. So NGK developed these batteries in a commercially. They're selling it. So far, 700 megawatts or 5 gigawatt hours are deployed. Most of them in Japan, and there are some deployments also in the United States and the Europe. So as we discussed, this is a high temperature operation, right? 300 to 350 degrees C operation. So thermal management is important in these batteries. You lose about 15% of the heat due to thermal losses. It's typical. And you need an external heater for startup because initially you need to bring it to the temperature. Once it is running, then you don't need to supply any more heat. It can maintain it. These are targeted for 6 to 8 hours of storage. Energy density is about 115 watt hours per kilogram. They're shown more than 5,000 cycle life. Round trip efficiency is about 75% and 15-year life. These batteries are commercial actually. There are some safety issues with these batteries because you're handling two molten liquids. If there are any cracks or defects in the beta alumina ceramic tube, these two molten liquids can mix and then create explosions. Metallic sodium is combustible if it is exposed to moisture. Typically, these batteries are hermetically sealed and they are surrounded by sand in an insulating box. The box that is shown there, they make it like a 5 kilowatt hour modules with several cells combined in series and parallel to get the required power output. They had one major safety incident in Japan at the Tokyo Power. After that, they made a lot of improvements on this, and then since then, they really don't have any major safety accidents. They had a good control after that. Go to the next slide. Recently, BASF, a German chemical conglomerate, they wanted to get into energy storage area. They looked at a lot of different technologies and decided to go partner with NGK and commercialize their sodium sulfur batteries market in Europe. They really don't change a whole lot in the design. They made some minor changes, basic chemistry is same, and also cell is same. They made improvements in the safety aspects of it. And then they passed actually UL 9540A container level thermal runaway tests. They are trying to commercialize this battery. Go to the next slide. Another type is not coming yet, but yeah. Another type is sodium metal chloride batteries. They are also known as Zebra batteries. Zebra stands for Zero Emission Battery Research Alliance. It's originally developed in South Africa, but in the US also actually General Electric tried to commercialize these batteries for locomotive applications, and then they abandoned it after 5 years of putting a lot of money in it. These are commercial. Some companies are still selling them. They also require high temperature operation, like 250 to 300 degrees Celsius. The difference here is instead of molten sulfur, they use molten sodium salt. These are slightly safe compared to sodium sulfur batteries. Energy density is slightly higher. Other than that, they're pretty similar. Go to the next slide. These two are commercial, the ones I told you. And then these are pre-commercial, the next two I'm going to talk about. There are some companies trying to develop even lower temperature sodium, molten sodium batteries. One is the Edina Power. This is out of Ohio State University. The difference here is they're using a Nasicon solid electrolyte conductor instead of sodium ion conductor that use beta alumina, which is high temperature, which requires about 300 degrees C for sodium ion conductivity. Nasicon conducts at a lower temperature sodium ions. So about 150 to 125 degrees C is sufficient. The advantage is at this temperature you can use plastic seals. So they're going with a planar configuration and trying to develop these batteries. It is still in the pre-commercial to R&D stage. The next one. Next slide, please. This one is Enlighten. This is also in the early R&D stage. These guys came out of Ceramtech, which has a lot of experience in developing ceramic products and making Nasicon membranes. So here, the twist on this one is they're trying to make a flow battery actually. In the sulfur is in a sodium in a polysulfide on the cathode side, and the anode side they're using molten sodium and Nasicon membrane. It is still in the R&D stage with some government contracts. They are developing this battery. Go to the next slide. Now we are switching gears to the low temperature sodium ion batteries, because until now we talked about high temperature batteries. These are in the low temperature batteries. These are very similar to the lithium-ion batteries. So you have a anode, either carbon or one of these layered oxides, and a cathode sodium ions intercalate between the they shuttle between the anode and cathode. Cathodes are sodium-based metals of different types, and anodes are hard carbon, some intercalation oxides, conversion alloys. There are 3 different types. And cathodes, I showed you, there are 3 different types there too. Electrolytes are, most of them are organic. There are few systems with aqueous electrolytes also. And the separator is polymer membrane, very similar to lithium-ion battery. And one difference is current collector. In lithium-ion battery, you have a copper current collector on the anode side and aluminum on the cathode side, whereas these batteries use aluminum on both sides, which is cheaper and also easier to maintain. So during charging, sodium ions move from cathode to anode, and the reverse occurs during discharge. In lithium-ion batteries, they shuttle between the graphite and the layered perovskites. The graphite anodes used in the lithium-ion are not suitable for sodium-ion. They fail very easily during cycling. You need a hard carbon, which is actually disordered carbon for the sodium-ion batteries. Sodium ions are slightly bigger than lithium-ion batteries, and they put more stress on the intercalation materials. As Dr. Gyuk pointed out, several Chinese companies such as Haina, CATL, Ferrasis, they announced mass production plans for commercialization. In the Europe, Faradian, Northvolt, TMET are working on it, and the US Natron Energy, which you're going to hear more about it in the later talks. Yeah, go to the next slide. So how do these batteries compare with other batteries in performance? So here I'm comparing with lead acid, nickel metal hydride, sodium ion, and 2 of the lithium ion batteries, LFP and NMC chemistries. So if you look at it, actually sodium ion batteries are performance comparable to LFP batteries in a lot of aspects. Actually, this is their biggest competition. They are definitely better than metal hydride batteries and lead acid batteries, but energy density is not as high as NMC yet. They have a wider operating temperature compared to lithium batteries. They operate at much lower temperature. And then, as I pointed out, they use current collectors the same on aluminum on both sides, so slightly lower cost. So the cost is here, I'm saying about 10 to 20% cost advantage for sodium ion compared to lithium ion batteries. Even though there is a big difference in the lithium carbonate and sodium carbonate cost, raw material cost, the sodium amount of lithium in a lithium ion battery is only about 7 to 8%. So rest of the components are all layered perovskites, current collectors, and the separator. So those don't change a whole lot. So the difference is in the lithium cost and the current collector cost. So about 10 to 20% cost advantage over lithium ion batteries. Go to the next slide, please. So the choice of materials. In the anodes, you see 3 types people are using it, developing sodium ion batteries. One is hard carbon, as I mentioned. The other one is titanium-based, some intercalation oxides. And the third one is conversion alloying anodes. So the first 2 are just sodium ions, the shuttle in and out, intercalation methods. The third one is really reaction and forming a alloying. So sodium is known to react with alloys with tin, lead, different group 4 and 5 elements. In this case, you're really forming an alloy, so you're destroying the structure and forming the structure, bond breaking. But the advantage is it has a higher energy density, it has a huge volume change also. There is one company, Unigrid, out of UC San Diego, is developing lithium sodium ion batteries with the conversion alloying anode. Go to the next slide, please. On the cathodes, again, there are, you see 3 different types, layered oxides. Faradian is using that one, and polyanionic, TMET, and Persian blue, Natron Energy is using that. The differences are depending upon the type of anode and cathode you use. Battery energy density changes and also the cycle life. Electrolytes, most of them are using organic solvents with sodium salts. Very typical as in lithium-ion batteries, ethylene carbonate and propylene carbonate. Only the difference is in the salts. Instead of lithium salts, they use sodium salt, like sodium chloride or sodium chlorophosphate. Only Natron is using aqueous electrolyte. It has advantages, but it has a lower cell voltage with the aqueous electrolytes. So the energy density is slightly lower, but it's safe compared to organic electrolytes. Yeah, we already touched on the current collector. Lithium-ion batteries need copper at the anode, aluminum at the cathode, copper at the anode. Whereas aluminum is used at both anode and cathode in sodium-ion batteries. Go to the next slide. Yeah, this shows a schematic summary of the things we just discussed. So on the anode side, there are 3 different types of anodes: hard carbon, intercalation oxides, and then our conversion alloying anodes. On the cathode side, you have a transition metal oxides, or polyanions, or Persian blue. Electrolytes are aqueous or non-aqueous. Most of them are non-aqueous, and we see only few aqueous electrolytes. Go to the next slide. Here I try to summarize, based on the literature information, some of the different types of sodium-ion batteries that are currently being developed by Faradian, Tiamat, Haina, and Natron Energy. Anodes, all the first 3 uses hard carbon, except Natron uses Persian blue. That is the only company using Persian blue analogs for both anode and cathode. Faradian is using layered oxide, Tiamat is polyanionic. Electrolyte, first 3 are using organic electrolytes. The Natron is using aqueous electrolyte. So you can see that voltage is lower compared to the other ones. So because of that one, energy density is low. But if you look at the cycle life, they showed very high, large cycle life. This Natron, the Persian blue analogs, has 3D structures with a large, let's say, cavities for the transport in and out of sodium ions. Because of that one, it puts less stress on the material. It has a large cycle life. Go to the next one slide. So this is my last slide. So compared to lithium-ion batteries, sodium-ion batteries are lower in cost and uses earth-abundant materials. It doesn't use any lithium, cobalt, and very low or no nickel in it. It utilizes aluminum current collectors on both sides. So the main differences between these two are in the cathode materials and the current collectors. Because of that one, the manufacturing process are also very similar. So we have a 10 to 20% cost advantage over lithium-ion batteries because of this lower raw material cost. They have a lower energy density compared to NMC batteries, but the performance is comparable to LFP batteries, which is their main competition. They offer better low temperature performance compared to lithium-ion batteries, and they can be stored and transported in 0-volt state, so it's much safer for transportation. Whereas lithium-ion batteries, you always have to store under some minimum charge. As I discussed a little bit earlier, sodium ions are larger than lithium ions. It puts more stress in the anode and cathode during intercalation, leading to structural failures during charge and discharge. So cycle life is one of the important criteria. Except Persian blue analogs, they have a good cycle life. The main challenges with sodium-ion batteries are increasing the cycle life, increasing the energy density, and scaling up for high volume manufacturing, which you're going to hear a little bit more from Natron. That's all I have. Thank you for listening. I'll pass on to the next speaker, Alex.
Thank you, Ramesh. While we're bringing Alex and his slides up, I just want to remind everybody that you should type your questions in as they occur to you. And we don't have very many questions yet. So if you have questions about sodium-ion batteries or anything else that's relevant, please go ahead and type those in. We're going to hear from Alex Bates from Sandia on safety issues, and then from Jack from Natron on commercial markets and applications.
Hello, good morning, good afternoon. Thank you for the introduction and thank you for the opportunity to present here. My name is Alex Bates. I am a staff scientist at Sandia National Lab, and I work in our battery abuse testing lab. And today I'll show you some of our work on commercial sodium-ion safety testing. Yeah, it seems to have trouble with advancing on my end as well. Yeah, okay. So I wanted to give a little background on Sandia's safety testing program for those that are not familiar. We have two primary safety testing locations at Sandia. One is our BAT lab. It's on the left. That's our battery abuse testing lab. Within that facility, we can do up to 1 kilowatt hour. So that's single cells and small packs. We can do any type of abuse initiation that you can think of. That includes nail penetrations, overcharge, over discharge. We are an R&D lab at heart, so we can do weird things too. For instance, we had a customer that requested a laser initiation of runaway. They were trying to mimic an internal short circuit, and we were successful in completing that task for our customer. The top right is our burn site facility. It's a bunker out in the middle of the desert. Within that facility, we can do up to 100 kilowatt hours. Recently, we completed a 25 kilowatt hour rack level test at that facility with the support of Office of Electricity funding, which that was quite exciting. We also work with a group called Fire Sciences at Sandia. Those are the open tests with all the flame that you see in that top right image. Within that facility, we can do basically any size that you would request. The bottom right is some of our accelerated rate calorimeters. We have 6 at Sandia, so we can do calorimetry from anything from material scale all the way up through larger pouch cells. Next slide. So this is just a demonstration reel of some of the testing at Sandia. So if you can go ahead and play the video, I'll talk through it. All right, so this is a 100 amp hour NMC crush test. So NMC rechargeable lithium-ion battery. It causes internal shorting of the layers almost immediately, and of course the cell does not like that, and it burns. This is nail penetration, and it's a similar effect, but different on the can. In that case, you see a lot of swelling. So the pressure increase is too rapid. This is a thermal ramp. It's surrounded by a heated jacket. So again, 100. We do have the vented gas going through the vent port. And then the next test is a 5-cell pack of LCO. And this is to look at propagation rate. So we initiate. Overcharges tend to be pretty abrupt, but of course it did propagate through, and we can see the rate of that propagation from cell to cell. This is the bunker. So this is the burn site out in the middle of the desert. This is a 3-cell 100 amp hour NMC pack. We're trying to look at propagation from cell to cell if we In this case, the thin sheet of metal was capable of preventing that cell-to-cell propagation. So you can bring the slides back up. There are a fair amount of videos in this presentation, so please bear with us. This slide is to demonstrate that Sandia does safety from materials level all the way through codes and standards. My colleague, Lorraine Torres Castro, co-wrote the US ABC Safety Testing Manual. I like to highlight the center bubble, that's simulations and modeling. We do expensive testing, so we make every effort that we can to take that data and utilize that data in simulations and modeling. I can go ahead and go to the next slide. So that's it about Sandia's capability. So we'll move right into sodium ion safety. As Ramesh mentioned, sodium ion is intriguing because of potentials for lower materials cost. It also has similar performance to lithium ion. And one of the key factors is that it has similar fabrication requirements. So it's kind of plug and play. You can go ahead and click through, I think, twice just to bring everything up.
Actually, before we start the next video, we have a lot of comments that the videos are so loud that we can't hear you speaking. I personally cannot hear you speaking while the videos are playing either. So can we turn the video sound down or even off? I think it's more important to hear what your comments are than to hear something exploding. And also, when you do these, could you explain a little bit more clearly what is the technology that's being tested? A lot of people don't know these acronyms, so it goes by very quickly, and it's not clear which technologies are which here. Thank you.
Sure. Yeah. So just to highlight the previous video, so that's largely to show Sandia's capability. The large prismatic cells were nickel, manganese, cobalt, so the NMC variety. So they were standard commercial lithium-ion technology, so nothing new there. And then the one with the smaller pouch cells, that was a lithium cobalt oxide, or an LCO type pouch cell. Again, that's a commercialized version of a modern lithium-ion battery. So hopefully that helps a little bit. Okay, so sodium ion. Sodium ion is a new technology. It's been advertised pretty frequently as safe, but we're still largely don't know the safety repercussions of these types of cells. So we were able to obtain some commercial cells through an online vendor. Of course, that's overseas vendor. So we did destructive testing on the on the sodium ion 18650 cells. They're 1.5 amp hour, commercially purchased, and we compared those to a 1.5 amp hour conventional lithium ion 18650. And 18650 is the cylindrical type, so the ones that you see in Teslas, or at least a little bit smaller version of those. And also both commercially purchased. And then next, I'll give you a little introduction on material scale analysis at Sandia. So next slide. So I'd like to preface this: sodium ion is commercialized. It has been commercialized by a Chinese company. They have a 10 megawatt hour grid infrastructure or grid installation that went operational May 11th. And they're planning to increase that to 100 megawatt hours. Next slide. Yeah, click again. So the iteration that we got is what's shown here. We received these at 1.5 amp hours. We tested them. They came out experimentally at 1.43 amp hours. If you look at that in terms of energy density, you get 123 watt hours per kilogram. That's with the case. However, if you're not familiar with these numbers, that's pretty substantially lower than a modern commercial lithium ion. We did some materials characterization. So we took the can apart, took all the materials out, did characterization. We found this to be the layered metal oxide variety. So if you recall from Ramesh's slide, there's a layered metal oxide, there's a Prussian blue, and there's a polyanion version of current cathodes for these cells. This is the layered metal oxide iteration. As he also mentioned, hard carbon is pretty prevalent. These were hard carbon anode. The salt is kind of a corollary to lithium ion, which is LiPF6. In this case, it's NaPF6 or sodium. And then the solvent that you see there is a combination of typical organic solvents that you would see in a standard lithium-ion battery. So there's almost no difference in the type of solvent in this cell between sodium-ion and lithium-ion. Next. Yeah, these are just some companies that I pulled from around the world. Of course, you're going to see Natron next. But you can see most other companies typically use a hard carbon anode and an organic type solvent. Natron is kind of the outlier, in at least in the terms of this table. But you do see that there is a wide variety of cathodes from across these companies. And I just like to highlight that the different cathodes will have an impact on safety outcome. Next. I think we have another video. Yep. So this is sodium ion 18650, commercially purchased from an overseas vendor, and we're doing a nail penetration on this cell. Yeah, most of the rest of the videos are pretty quick, pretty abrupt. You can go ahead and bring the slides back up. So as you saw, that nail penetration was quite destructive. There was a rapid increase in pressure that blew the cell apart. You can go ahead and go to the next slide. And it removed it from the fixturing, and it actually broke that nail off of the holder. So this slide, or this slide layout, is what I'll show for the rest of the presentations, or for the rest of the destructive methods. The left side will always be sodium ion. The right side will always be lithium ion. The blue curve is the voltage, so you can see the point at which voltage was lost in the cell. And then the other colors are thermocouples that are attached to the outside of the cell that are showing the temperature obtained. So for that nail penetration, the sodium ion got to 216 degrees, where the lithium ion got only to 98. Now, there's a bit of an asterisk here. NMC cells do tend to be pretty destructive under nail penetrations, but this cell was quite low in capacity compared to modern lithium ion NMCs. And so we believe that's why the lower temperature was obtained. Of course, you saw in the video, the sodium ion was quite destructive in its failure response. There was sparks, smoke, venting, and it broke itself free from that fixturing. We can probably skip the next video just for brevity. The next video was just zoomed in. So go ahead and go, 2 slides. It was just a zoomed in version of the exact same failure. As you can see, the cell did not explode. The contents of the cell are still largely contained within the cell. The lid ruptured, the lid came off of the cell, but the contents are still contained within. Next slide. So the next test we did, we call a crush test, or a mechanical crush. This one is a video, so you can go ahead and bring that up. We have a hammer type implement that we drive into the cell. So we're just simply pushing that round bar into the cell horizontally. Yeah, that's the slowed down version of the nail penetration. I like to show that in live presentations because it's kind of more dramatic. But yeah, go ahead and play the next video. So as you can see, it's kind of a similar response to the nail penetration. The hammer implement was holding the cell in place, so it didn't remove itself from the fixturing. But you got a similar response, that kind of rapid pressure increase that blows the lid of the can off. Yeah, thank you. And then you also saw that there was a smoldering ember next to the cell, and that actually caught the vent gases on fire. So they are flammable under the right conditions, which we would expect because, as I said previously, it is a mixture of typical organic solvents that you would see even in a lithium-ion battery. So these are the quantitative results of that test. The right side is the max temperature of lithium-ion at 300 degrees C. So the lithium-ion in this case actually did get hotter. Sodium ion only got to 168, but they both had the same observable failure. They both had this venting, smoking, and the lid of the can popped off in both cases. Next. So the aftermath of this one, you can see that some of the contents did come out of the cell, so they're not all inside of the cell. But again, it didn't explode, just the lid came off violently. I like to show this, the bottom or the right side image. You see the red circles on kind of the bottom right. There's normally a door closed during this test, and that door was closed. But when we came in, we found the cap of the 18650 had actually ejected all the way out of the bay underneath that door. Next. So we're moving on to a different type of test. This is an external short circuit. So we have the cell fixed to some a circuit that we close, and when we close, it allows the cell to dump all of its energy almost immediately. The lithium ion and the sodium ion both got to about similar temperatures, around 140 degrees C. The lithium ion only swelled, but the sodium ion actually smoked, vented, and had electrolyte leaking out. And it discharged 159% more capacity than the lithium ion. So next we have another video. You can go ahead and play that one. Normally for external shorts, we don't see a whole lot. So it was a little surprising to actually get a vent, a diffused vent in this external short. So at first you'll hear a loud sound. It's the external contactors closing. You will see a little bit of smoke that's from the fixturing getting too hot, but then you'll hear an audible pop that's from the vent itself. And then if you look below the fixture at the vent, you'll see some leaked electrolyte. Okay, so as I described from the external short, the sodium ion was more, it showed us more than the lithium ion. Like I said, there was a vent and leaking, which we don't normally see for lithium ion. So that was interesting. And I think it's a product of what Ramesh said, the sodium ion cells, they can be a little bit more performance based in the discharge aspect, which, as I said, we discharged more in that external short. So we see that. This is a thermal ramp. Sorry if you're hearing background noise. This is a thermal ramp. We got about the same max temperature for both lithium ion and sodium ion. We also had the same onset temperatures for the different kind of effects. So voltage drop occurred about the same temperature. Venting occurred about the same temperature, and thermal runaway also occurred about the same temperature for both cells. We were a little perplexed by this at first. We actually did a repeat test just to make sure that this was valid, but it is, and if you think about it a little bit more, it makes some sense. Both of these sodium ion and lithium ion cells are layered metal oxide cathodes. They both have a carbon-containing anode, and they both have organic liquid electrolytes. So there's a very similar corollary and composition between both 18650 cells. Next. And I think there's another video of the thermal ramp. 150 degrees C. Vent. All right, we move on. So that wasn't a distinct thermal runaway in terms of sparks and fire. Although if you notice the temperature above the box, we did increase from 300 degrees Celsius to 400 degrees Celsius quite rapidly. And so depending on who you ask, we do term that a thermal runaway. So again, it wasn't in terms of fire, but we did get a rapid increase in temperature. So next we did an overcharge. The overcharge was largely uneventful. We only hit 75 degrees Celsius. We hit what we call compliance voltage at 194% SOC. What that means is the power supply charging the cell just polarizes and the cell goes straight up in voltage. And there was no observable event for overcharge. Now, when we have an overcharged cell and we have zero voltage, we have to do something with that cell, and we have to make sure that cell is safe to handle and to discard. And so for that, we did what we did a crush test, which is what I showed you previously. There is a video here, and if you can get this one to play, this is kind of the most dramatic video. So this is a crush of an overcharged cell. So theoretically, it contains a lot more energy than just a normal 100% SOC cell. There's no sound on this one, but if we can get it to play, you'll see that there is a lot of sparks and flames that do come from this sodium ion. So this one self-ignites. So again, lots of fire and flame there. All right, next we did an over discharge. So instead of bringing it high above 100% at SOC, we brought it well below 0% SOC. And again, this one was largely uneventful. That is the last of the video, so we'll just have to get through slide transitions after this. So this one, again, uneventful, no major heating, just 52 degrees Celsius. We also did a post-over discharge crush on this one just to make sure it was safe. And in this case, it was safe. We didn't see any, we had an IR camera, infrared camera on it, and we saw no signs of heating, just some liquid electrolyte leaking out because we're mechanically crushing it. Next. So unfortunately, I have a lot of slide transitions here, so I think I'll just talk through it as is, and then you can kind of go to the end after. So just in summary, we had a nail penetration, which is a pretty standard abuse test. We got a hotter temperature with sodium ion, and we got a much more violent response. If you recall, this is the one that broke the nail off the fixture. Then we did a crush test. In the crush test, the lithium ion did get quite a bit hotter than sodium ion. However, the sodium ion required less crush depth, so we went into the cell a lesser distance for the sodium ion to get that runaway initiation. Both cells responded similar observable response. And then we did an external short circuit. They both got about the same temperature, but as I mentioned, the sodium ion cell actually had the audible vent with flammable gas release and liquid electrolyte coming out of the cell. And the last test that I'm summarizing here, at least the one that we compared to lithium ion, is thermal ramp. And interestingly, we got a very similar response between both lithium ion and sodium ion. So you can go ahead and start tabbing through those slide transitions. The key takeaway here is that sodium ion is not good under mechanical failure. Mechanical failure tends to result in this rapid pressure increase and destruction. And we also had a more robust failure under external short circuit for sodium ion than lithium ion. Next. Okay, so I like to preface this next section, and I'll try to go through this quickly because I think we're kind of hitting some time constraints. Maybe we have one more presentation. This is the Ford EcoStar. So I don't know how many of you have seen the Ford EcoStar, but sodium sulfur technology was first looked at Ford in 1965. And then it was researched off and on for about 30 years. And then in 93, they decided to make 100 prototype EcoStars. This was a sodium sulfur technology, so totally different than what we have today. But these cars were expensive. They were hand built, and they took a lot of time, a lot of research hours to make. But unfortunately, between 93 and 96, 2 of these vehicles caught fire while charging. And then in 97, Ford shut down the program entirely. So of course, they definitely learned a lot through this whole process, but at the end of the day, they had nothing that they could profit from. So a lot of time, energy, and money went into this development with nothing to show at the end in terms of profitability. The reason I like to show this is at Sandia, we are very interested in safety at the material scale. Now, if Ford had access to some of the capabilities that we have now, they may have done some materials level analysis that gave them insight into why this failure happened or why this failure could happen. And they may have made some different changes in the direction of the program. They could have implemented more engineering controls, or they could have better made some changes at the material scale to prevent this kind of destructive failure. Next slide. Okay, so this is, again, as I said, material scale approach to safety analysis. This is kind of a new area of research at Sandia and even across the whole research field. At Sandia, we're looking at a handful of new chemistries, things like lithium sulfur, sodium ion, solid state batteries, and we're using this similar material scale approach. So this slide is meant to be a demonstration of how this works. The red curve is using what we call a microcell, and this is differential scanning calorimetry. So it's a calorimetric technique. We're taking all of the layers of a sodium-ion battery, and we're stacking them and putting them into a sample pan, with the caveat that they are only 4 millimeters in diameter, so very small amounts of material. The blue curve is thermogravimetric analysis. What the blue curve is telling us is when mass loss occurs. So when are things decomposing and giving off other constituents? So if you go ahead and go, I think four slide transitions forward, I'll just talk through. So this first point is the boiling point of DMC. It's at 90 degrees C. Right after that boiling point, you see this kind of red curve. That's a heat flow. And then we have boiling point of EMC at 107. Right after that point, you see another bump in the red curve that's larger. That's a larger heat flow. And then at 200 degrees C, we have boiling point of PC, EC, and within this largest red hill here, we have cathode mass loss. So what does this mean? So at these distinct points in temperature, we now have an understanding of what reactive materials are present at that time, what heat flows are there, and then with that information, we can start to think about reaction pathways. So we can hypothesize which reactions are causing each of these red hills or mountains. And then with that information, if we can identify which one is critical for that largest mountain, then we can start to inform on what materials need to be changed. So for instance, if you know that your liquid electrolyte or one constituent component of your liquid electrolyte is causing this huge exotherm, maybe you want to change that component, or maybe you want to change that additive, or so on and so forth. The bigger picture here is not just a microcell, but showing cathode only, cathode plus liquid electrolyte, anode only, et cetera, et cetera, et cetera. With that bigger picture, we can start to compile all this data together and get a really clear view of the reaction pathway. Go ahead and go to the next slide. Okay, so again, I put way too many slide transitions in this here, so there's quite a few. I'll try to talk through this briefly. This is accelerated rate calorimetry. This is what we call, it utilizes what we call a heat weight seek mode. That heat weight seek mode just means that the arc is looking for self-heating. It's all adiabatic. It pumps the heat up incrementally, and then it looks to see if there's a response from the cell. The cell is actually heating itself. We see one self-heating event at 105. So this one is not strong enough to make the cell go into runaway. So the system goes back into heat weight seek. We see another self-heating event at 120. Now this one does sustain. It leads into a vent, and then a thermal runaway at 189. A pressure ramp, and then our maximum temperature of 480. So now you can go ahead and go straight through to the next slide. So why am I showing you ARC? So I'm showing you ARC to compare to the DSC. So the top plot is a full 18650 cell. So that's the cell that we purchased, we got in our hands, we stuck it in the ARC, and then we ramped up the temperature and looked at the response. The bottom one is the one that is only 4 millimeters diameter. So just very small sample sizes and a calorimeter. And so what I want to show here, I want to demonstrate, is that there is a corollary between the materials and this large scale response. So next. So you're going to see a line pop up. Oh, did we just, yeah. So the first dashed line corresponds with self-heating in the full 18650 and the small exotherm in the DSC. The second dashed line corresponds with the second self-heating and the medium-sized exotherm in DSC. And then the next dashed line at 200 degrees C corresponds with the onset to thermal runaway, which also is the onset to this largest exotherm. So now we have a direct corollary between a very large exotherm at a very small scale and an actual thermal runaway in a real 18650 battery. Next. I think this is pretty much the end, so I have a couple things to point out. Actually, this is an important slide. So Rachel Carter at U.S. Naval Research Labs has also done testing on sodium-ion batteries. The red curve, so this is ARC, similar to what I showed you before. The red curve is the same cells that we had at Sandia. And her results on this ARC testing correlate very well with our results. We're seeing the same things. But the reason I like to show this slide is that the blue curve is a Prussian blue iteration of sodium ion, and the green curve is a polyanion iteration of sodium ion. And you can see that the blue and green curves have a very different response to that red curve. The blue curve has a much higher temperature till it actually hits a self-heating event, and the maximum temperature is quite low compared to the layered metal oxide. And so what I mean to demonstrate here is that not all sodium ion batteries are created equally. The current version of commercial sodium ion appears to be quite dangerous and even on par with lithium ion. However, other types of sodium ion, it appears, may be much safer than the type of sodium ion that we got at Sandia. Next. Sodium ion is doing a cycling reliability study. If you're familiar with some work that Dr. Gyuk has supported at Sandia for quite some time, they did this for lithium ion. Yes, of course, I'm almost done. And we're doing a very similar study for sodium ion, also funded by the Office of Electricity. Go ahead, next slide. I think that pretty much concludes it. I wanted to thank my team at Sandia, Lorraine Torres Castro and Nathan Johnson, our postdoc that works on this. The next slide is the acknowledgments for Department of Energy's Office of Electricity for funding support of this work. And I think that concludes the presentation.
Thank you, Alex.
Thank you, Jack Pouchet with Natron. Alex, that was a great comment about not all sodium ion batteries are made the same. For that matter, as we know, not all batteries are made the same. So some great intros, some great conversations and discussions about the technical aspects of batteries. Today we're going to talk about sodium ion from the Prussian blue, but I'm going to also speak a little bit about some of the other chemistries that are out there. Natron, founded in 2012, just turning the corner on commercialization with our new factory in Holland, Michigan. We'll talk a little bit more about that. Focused in on the Prussian blues, safe chemistry, safe batteries. Let's move on, and we'll go back. We'll continue on. So next slide. So really phenomenal videos, and that's exactly why my wife refuses to drive an electric vehicle. Nobody wants a bomb in their garage. Regardless of chemistry, it doesn't matter whether it's lead, lithium, NiCad, certain sodiums, as we saw, nickel, zinc, et cetera, et cetera, et cetera. All batteries have different unique performance characteristics. What we want to do is identify the proper risk, proper performance, proper characteristics we want for application. And I believe we started all of this off with stationary power. I'm going to challenge the energy density question right up front, because to us it's immaterial if you're looking at stationary power. Real estate's cheap. Safety is not. Loss of life is not. Loss of materials is not. Environmental impact requirements. Looking at the humanistic element, right? What are we doing to indigenous peoples as we source raw materials? There's a host of factors, but what we do know is many batteries out there have poor performance characteristics. Let's move on to the next slide. So when we look specifically at Prussian blue analog sodium ion batteries, we eliminate many issues that we have with batteries. As previously noted by the other speakers, we don't get energy density. That's fine. Stationary power we're talking about here, and many other applications, military, industrial power applications where space is really not a constraint. Loss of life, loss of materials, those are critical. High cycle rate, as noted by a few others. When we get into the Prussian blue analogs, we're going to get more specific on that in a moment. You get the benefit of very low internal impedance, very, very high cycle rate. Move on to the next, and I'm trying to accelerate my rate of speaking, so please bear with me. Got a couple other things, and CATL and Hynop brought this up a couple of years ago. One of the benefits of sodium ion when we look at the EV application, of course, it does involve hard carbon and thermal runaway, but you can charge it at low temperatures. With Prussian blue, you can charge at -50. You You can discharge at -50. You can also run at very high temperatures. So you get a really wide dynamic range. Again, stationary power, what does that mean? Well, the lower cost of installation. You don't have to keep these things as cool. You don't have to keep them as hot in the wintertime, right? So when you look at the overall system benefits, you might find that when you look at sodium-ion batteries, there's unique benefits that you get at a total system installation cost point. Let's move on. We'll go on to safety. And I really appreciate those videos. Those were phenomenal. Folks, if you go to Natron's website, you can see some incredible videos. We model most of the UL 9548 testing, the nail penetration test, love it. I'll just share with you, every safety agency that has tested our battery so far has said it is the most boring battery that they have ever tested. We have taken them up over 350 degrees Celsius, and they still put out voltage. We actually had the electrodes burn, not on the cell, but the test equipment. Projectile testing, nothing like shooting it with a 5.56 or a 7.62 round bullet and finding that nothing happens. There's no acid leak, there's no outgassing, there's no hazardous materials, and the cell or battery continues to perform. Next. Next slide. Okay, so there we go. Again, Prussian blue analogs. Not all sodium-ion batteries are created equally, as was previously noted. With Prussian blue analogs, we can ship these fully charged anywhere in the world by air, right? So that safety also translates into speed of installation, speed of use, because if you can get your battery to a site fully charged, you might save anywhere from 8 hours to 2 days. 2 days would be a nickel zinc battery, but you might be saving up to 2 days to get that system up and fully charged, right? You're good to go. Some huge benefits there. Next. I want to get a little bit into some of the technology. Thank you. So, with Prussian blue, intercalation is not a problem. So if we hone in on, and we're not going to put it on this slide, but if you hone in on the lattice structure of the Prussian blue framework, you see it is a space roughly about 1.2 angstroms. And if we look at the sodium ion, it's 0.9. So the beauty is that we can intercalate with ease. The internal impedance is somewhere between 1/4 to 1/10 of what we see in traditional lithium ion or other battery chemistries. And that allows for rapid charge, rapid discharge, no deformation, no requirements for SCI layers, high cycle count, no thermal buildup. I mean, it is a unique set of properties. What do we give up? As previously noted in the other slides, you give up energy density. We're talking stationary power, folks. Land's cheap. All right, next slide. Yeah, so as I said, so what do we get benefits? Rapid charge or discharge. When I say rapid charge, we're talking about an endothermic reaction when you do charge. Not exothermic, endothermic, right? So you heat it up a little bit, and remember, very low internal impedance. So 98, 99% round trip efficiency on these cells. You're not getting a lot of heat on discharge. And when you go to recharge, it's cooling off. Again, net benefits, rapid recharge, 8 to 10 minutes to full charge, provided you've got the current to do that. So you have a battery that can cycle a lot, can operate over a wide temperature range. And I'm just going to talk cycles for a second. This is becoming public information. We have now tested over 1 million cycles. Okay, now that's a special load profile, but that's beyond ultracap territories that we're in with very minimal degradation. Next slide. And I'm trying to be aware of time. So let's move on to, yeah, thanks. We're going to tee up next one. So I really like looking at what goes into batteries, right? I mean, when we really dig into LMC or NMC, LCO, I mean, come on, we got cobalt right there in the middle of the forehead, big C there. Whether it's cobalt, whether it's, and all of the issues associated with the mining practices, the human elements involved with it. Lithium. And lithium is the poster child of digging up hundreds of thousands of pounds to make a battery, displacing indigenous peoples around the world, watersheds. I mean, this is not a good way to treat the earth or to treat our people, but we need what it does, right? I mean, we all benefit from, sorry, that's my phone. We all benefit from the mobility we get with lithium. So let's put lithium where it belongs. Let's continue to use it where we need it. But let's not try to force lithium into places where other solutions, whether it's sodium ion, sodium sulfur, sodium metal, sodium nickel chloride, or other chemistries, right? Let's make certain that we're doing the best thing we can for the environment, for the people. Move on. So, yeah, thanks. So supply chain, made in America. I mean, at least where we are with we know that CATL and Hainan, BYD and others are doing, the French are doing sodium ion chemistries. We know the UK, India. I mean, it's being developed around the world. Prussian blue, a lot of patents, a lot of protection, made in the United States. Santa Clara, Holland, Michigan. Natron announced Gigafactory in North Carolina for a 2027 timeframe. So very excited about the batteries being made here, but more importantly, the raw materials for the batteries can and are being sourced in the United States. And as we look at what's going on around the globe, we certainly want to take advantage of local resources as much as possible. I don't plan to buy land in Wyoming, but I do appreciate the insight to how much sodium carbonate is available in Wyoming. When we look at this in terms of what's available in terms of supply chain, logistics, there's a tremendous amount of benefits. The interesting thing, at least from our perspective, is that with Prussian blue analogs and most designs of sodium ion technologies, you can put these into a lithium ion factory. So you're not reinventing the wheel, you're not creating a new framework and a new platform from a manufacturing perspective, right? You don't need new equipment, right? You use very similar equipment. You do plate thicker, so we didn't get into that. I'm looking at the time clock and I realize people are going to have questions. So when you're spraying the electrode materials, it is significantly thicker than lithium ion, which does mean pouch cells is your preferred choice. You end up with, you end up with a cell that feels prismatic. It's very hard. It's a semi-aqueous, it's a paste chemistry that gets about 95 to 98% absorbed within the Prussian blue, being a giant sponge. So it's a very interesting process, lends itself to volume manufacturing. Again, very simple materials, very simple process. If someone has run a lithium-ion battery plant before, you eliminate a couple steps. You don't have an SCI boundary layer. You don't have a formation step, so you take that out of the factory, and pretty much everything else looks very similar to what you would see in a lithium-ion factory. But we'll move on. And again, supply chain, very easily controlled, can be duplicated on other continents. So we can cut and paste what's done in the United States, move it to EMEA, move it to Southeast Asia, very simple to go. Fast forward, sorry, next slide, just so I don't want to get too commercial here. Talk about some products. So Natron is commercial. We are shipping a 48-volt battery pack, 25 kilowatts. Back to the energy density, that's about 1.2 kilowatt hours. So We have developed a power battery. We are not interested in 4-hour, 8-hour, 12-hour discharge. I'm going to talk in a moment about other people who are with sodium-ion chemistries. There's some brilliant chemistries out there for 8-hour, 10-hour, 12-hour, applications. Natron is focused in on peak shaving, short duration, defense applications where you need a tremendous amount of power in a very short period of time, data centers, etc. And that's a product that we are shipping today out of our facility in Holland, Michigan. Next. And related to that is we take it, put it in a big battery cabinet. So you take one, put 10 together, you got a string, 250 kW at a 2-minute discharge, 340, 350 kW to 1-minute discharge. We don't discuss how much power you can do in a very, very short, because it's all related to how much copper you can put on the system. And system impedance is not battery impedance, but people are cycling it for incredibly short duration applications. 5 to 10 minutes is probably the range of how far you want to go. Again, this is not intended to be a 4-hour, 8-hour, 12-hour battery. Short duration. Next. So, as I said, what are the applications where we're at? We're shipping these into data centers today, typically bridging to another energy source. So you're either going to diesel gensets, natural gas gensets. You could be going to fuel cells, which have somewhere between, PEMs 42 seconds to get the 50 seconds to get the full power. Solid oxides much longer, or other, renewable energy source system. You could be going to a low battery. You still have bridging and you still have peak power applications where a sodium-ion battery fits in. Next. So peak shaving, microgrids, talking about this is an oil and gas platform, but the basic concept is as we look at peak shaving, you need to be able to use it many, many times. And this is where lithium falls short because it takes a long time to recharge, doesn't like being dissipated very, very quickly. Sodium-ion excels. Next. And I kind of hinted at microgrids with the oil and gas platform, but microgrid applications, industrial applications, dark start applications, high peak power. We tell people, I tell them all the time, if you had a 1 megawatt hour rated Prussian blue sodium-ion battery, I'm going to have 30 to 50 megawatts of peak capacity. So dark start. Next. There was a next. Did we lose it? Did we lose the next slide? I don't know what we have. I don't see it anymore. Went away.
Jack, I'm seeing a slide that has other sodium chemistries and / batteries on it.
Thank you. Yeah, it went away on my screen. It just went black. So, as I said, there are other chemistries out there. A few people have spoken about them. Ferradium, ceramic, engineered for 4-hour, 8-hour, 12-hour discharge capacities. The former Physonic, they've now been acquired by a Swiss company. Sodium nickel chloride, high temperature battery. So not a sodium ion, but still a sodium battery. Again, long duration, discharge applications. Tiamat, I'm not going to say that was them, that was in the nice, wonderful Sandia test labs, but EV applications. And then, of course, there's Northvolt also going after EV. So we see people looking at adding sodium into the mix to address temperature, address charge, rapid charge, but we still have thermal runaway if we put a hard carbon anode on it, as was previously noted. And with that, I'll give it a wrap so that there's time for other people to ask questions. Thank you.
Great, thank you. If everyone could just bring their cameras back up, all the speakers. And we will, as I said earlier, we will extend the time a little bit to get to some questions. I apologize that we are a little over time, but I hope some of the participants can stick with us. Okay, first question. What will be the state of sodium battery commercialization in 5 years? Or if you prefer, when will we get more commercialized types of sodium batteries for various applications, stationary and EV and so forth?
Well, I'll jump on that for at least from the Prussian blue perspective. In 5 years' time, we're probably talking North America supply chain of 10 to 20 gigawatts worth of stationary power, peak power batteries. If we look at the EV world, it's going to be significantly higher than that, I think, out of China, with what CATL and BYD and Hyundai are attempting to do, Northvolt as well. So, I think you're going to see we already are seeing a bifurcation, EV and other applications.
I think from the top down, it means in 5 years we must have sodium because lithium is going to be used for cars.
Yeah.
Right. Okay. Well, that leads into the next question, which is, are advances in sodium-ion battery energy density anticipated such that they could be used in electric vehicles?
I'm going to say you can do it already. So it's just range. If people get over range anxiety, the cells that CATL and BYD have, it's enough energy density for a city car.
Yeah, a lot of companies are targeting for that, increasing the energy density, but it's a tough challenge, right? You have competition with LFP, unless you can show big advantage in cost and performance. It's very difficult. Of course, NMC is preferred for autos because of the range. The higher the energy density, less weight, longer range. So that's what is preferred for autos.
Okay, great. We saw a lot of images and some videos of various kinds of batteries being tested to the point of destruction. Question is, do sodium batteries that do catch fire take as long to be extinguished as lithium batteries? Is it a similar process? And we've seen, unfortunately, some cases where lithium batteries were going over thermal runaway, going over to the point where they are on fire, and there's some difficulty in getting them out. So what's the process with sodium?
Yeah, that's a great question. I really like that question. It's something that we talk about frequently, is how long these fires burn and how you can't really extinguish them, right? It's hard to tell at this point because the only version of sodium ion that we have is 1.5 amp hour 18650s, which is not close to state-of-the-art lithium ion. We don't see the same flame jets, sparking, and fires that we see with lithium ion, but we believe that's largely driven by that lower capacity. So if you increase energy density, increase capacity, make larger cells, you're probably going to see that same flame jet and sparking response from sodium ion, which indicates that it's similar reaction pathways, and they're probably going to burn for quite a while, similar to lithium ion. Now, again, this is for the layered metal oxide version of sodium ion that has that oxygen to give off and sustain that fire.
Yeah, and I'm going to suggest that until we see commercialization on the EV level, there are benefits to the sodium ion in that if you put it out, it doesn't self-reignite, unlike lithium.
Okay. Somebody wants to know about opportunities for sodium ion batteries to be reused and recycled. Is there a circular economy here, and are the sodium ion batteries that are being commercialized being designed for reuse and or recycling?
Yeah, so Todd, I can only speak to the Prussian blue ones right now. The core materials have little to no value. So the reason why we recycle lithium is it's very hard to get lithium, and it's very easy to get sodium. So we recycle lithium. We recycle it because of the cobalt, which is also very difficult to get. But when you look at the core materials that go into sodium ion, there's really not much there to recycle. And it's very easy to dispose of because the materials themselves are intrinsically safe.
Yeah, I agree. Also, it doesn't use copper too. Unless you have a lot of cobalt, nickel, expensive
Yeah,
materials, there is no
copper.
point in recycling. Yeah.
Yeah.
Okay. We've talked a lot in various webinars about the duration of lithium ion being, great for short duration applications and not so great for long duration applications. And there's a big effort right now to develop longer duration energy storage. What's the deal with sodium ion duration? Is it about the same as lithium? Is it more or less? You mentioned that your products, Jack, are really targeted toward very short duration applications, but
Right.
what's the real ability of the material and of the
Yeah.
technology?
Well, so a battery is a battery. In any battery, once you put energy in it, you can discharge it at whatever rate you want. So, I very specifically said we are optimized for very short, very high power applications, which lithium doesn't do. Right? You can discharge a lithium battery in over 2 minutes. Good luck if you try to get all the energy out of it in 2 minutes. It will explode. It will do bad things. So we've optimized it for those applications, but you can discharge it over 1, 4, 6, 10, 12 hours. It's just not really cost effective, space effective. It's not good use. Other sodium ion chemistries, again, I talk about the ceramic with ferradion. You look at the sodium nickel metal chloride. Look at other sodium sulfur, all designed for long duration discharges, and they do it really well. Right? So there's a different battery for different use cases.
Okay. Somebody wants to know whether the comparisons of sodium ion batteries with NMC batteries on the pressure and puncture tests, is that because LFP tests aren't nearly as exciting? I think the implication is that the lithium iron phosphate batteries may not explode when is that true, or is that just because that's the way you happen to do the testing?
Yeah, no, there's lots of caveats there, but largely we chose the NMC iteration because it was a layered metal oxide version that we expected to have at least somewhat similar response to the sodium ion, it turned out that it did. LFP certainly is less exciting in most destructive testing, especially things like thermal ramps and nail penetrations. Overcharge is where it can be a little bit more tricky and can actually result in things like runaway. But yeah, LFP is more robust in a lot of ways.
Okay, thank you. Somebody is asking about whether there's a way for sodium ion batteries to add energy density. And what they're saying is LFP batteries have been able to add energy density by moving to LMFP or L3P, and maybe you guys can define what that means. But the basic question is, are there ways for sodium batteries to catch up to those gains in energy density, or is there a fundamental physics problem that limits the energy density of sodium batteries?
No, there's a lot of research is going on that in that area. For example, the Unigrid, as talked about, out of UC San Diego, they are going after higher energy density, but it involves a reaction, conversion reaction, huge volume change. There are a lot of issues to deal with it in designing the battery. So you choose the right appropriate cathode and anode materials to increase energy density. That's what a lot of people are trying. I mean, there is no fundamental limit why you can't go higher.
Yeah, I would like to add, and I think this is an interesting thing that maybe doesn't get talked about enough, but outside of the chemical limitations of energy density, you also have the things like ancillary components. So you think about a full system. If your system is inherently safer, then you don't need the same thermal controls. You don't need the same engineering controls for things like runaway, and that's important and impactful in EVs and in grid storage, especially from a perspective of cost.
Yeah, and to further to Alex's point, it's not only the safety, it's also the temperature operating range and the amount of heat generated by the battery on charge discharge. So if you can pick up a few percentage points of efficiency, or a lot, maybe 5 percentage points of efficiency, and a wider operating range, that significantly reduces the balance of system.
Okay. Somebody is asking about cycle life. Is it significantly dependent on depth of discharge? And are the cycle lives that Ramesh reported discharging to 100% of depth of discharge or something else?
Cycle life depends on the um, type of materials that you choose, right? We talked about some of the layered oxides have a lower cycle life right now. They're failing easily compared to Persian blue has a large cycle life because it puts less stress on the material. But maybe you're talking about in the sodium sulfur batteries, that's a different reason why they don't go down to fully discharge. They stop at 1.75 because of some of the sodium polysulfides. They, they you cannot reverse them easily, and they
Right.
get deposited on the cathode, and full conversion doesn't happen. That's the reason they stop at a lower range. It affects the cycle life, yes, but when you talk about cycle life, mostly people talk about degradations, either material degradation or something like that. So, yeah.
Okay. And I think we have to wrap this up, but I'm going to ask this one last question. What large-scale demonstrations or pilots of sodium battery systems exist? Do we have any data from those?
The only
Yeah,
one I'm aware of is the one I showed from the Chinese company, the 10 megawatt hour installation. That's the only one that I've seen any news on.
yeah, there's the low temperature sodium ion, but high temperature, you get a lot of commercial data. It's a commercial product, right? From NGK and BASF is putting some of the demonstrations. Uh, it is commercial. Market is not huge at this stage because the cost is still high for them compared to other thing, and then because of the safety, some people are reluctant to put that one. I mean, even though they proved to be safe, but when it comes to high temperature, a lot of other things come into the picture. You had thermal losses associated with it, and then uh, so if you want to do a lot of uh, startup, and you need a heater to start it up, right? And if you maintain it at the temperature, it's okay discharging it. But if you not doing anything, battery sitting there, then it will cool down. Then you need to again put the heat. So there are some issues with the high temperature one because of those things. That's why it's not, market is not huge yet for that product.
Okay. Thank you, everybody. I think we are going to have to wrap this up. I do appreciate that all the speakers were able to stay an extra 15 minutes after an hour and a half webinar. It's very generous with your time. Thank you again. Zareen, do we have anything to announce?
We just have a few upcoming webinars that you can see on our website at cisa.org/webinars. Everyone will be receiving a recording of this webinar. Thanks again, everyone, and have a great afternoon.
Thank you.
Thank you.
Thank you.
Thank you.
Bye-bye.
Bye-bye.